Okay, so I think we'll get started. Again, a couple of reminders. This homework 3 will be due tomorrow. Okay, and then exam 1 will be on Wednesday next week. Okay. Um, so today's classroom disinfection I have assigned to Isaiah and Macy. All right. So today we are going to check chapters 3. So chapter 3 will not be on first exam, but 1 and 2, and then the chapters we talk about in volume 1 will be in exam 1. Okay. All right. So chapter 3 we'll be checking at thermodynamics, laws of thermodynamics. Um, so let's take a look first the definition of a thermodynamic system. Okay, so that's pretty much the anything that of your interest of their thermodynamics. So for example, if you have a container that has a gas inside it and you're interested in the thermodynamics of the system of the gas system, or could be something else like maybe a piece of say whatever metal or maybe some liquid inside system. Okay, now if you have a system that is completely separate from the environment, it's called an isolated or closed system. Um, so something like this, if you have a very well insulated, okay, container here, then this system, you may consider it as an isolated or closed system, okay? But in reality, that's not possible because in the immediate contact of the walls to the system, so this system has contact with the surrounding, okay? So in reality, you cannot have a real like isolated system, okay, in the real world. But if you can insulate so well, so then the heat exchange can be minimum, then you can kind of treat it as a closed or isolated system. Okay. Couple examples you may be seeing like on your daily basis, like a skittle for water or maybe a pressure cook like that. So then the inside, in this case, this is a not so well insulated system, and this is kind of like insulated system for the inside. Okay. All right. So that's pretty much the first section. The second section talks about the work, heat, and internal energy of the system. Okay. So for example, we'll start with the simplest case of an ideal gas if it's confined in a container like this. On this end over here, where this wall can be movable. Okay. So then if the gas expands, then it will push this wall in this direction. So then there will be certain work done by the gas to this wall over here, okay? So we can kind of see how much work is being done by the process. So take a small change in the distance of this wall is moving, dx. The force should be equal to the pressure times the area of this wall, okay? So then force times the distance, that should give you the amount of work done during that process. So dW equals to FDX, okay, for a small change in X. And that should be equal to P times A times dx, okay? Now, A times dx will be the change in the volume of the gas, okay? So then the work can be rewritten as pressure times D times volume change, okay? So then to calculate the total work done, you will be doing integration. If the volume expands from V1, the initial volume, to the final volume, then work should be equal to integration of V1 to V2 times P dV, okay? All right, so this is the general equation you can use to calculate the work done by the gas system to the surrounding. All right. Now, if this is the ideal gas, then you can apply ideal gas law of PV equal to nRT. So then in that case, P can be written as nRT over V. So if T is constant, all right, N and R and then T, they are all constant then in this case. So you can move the constant terms in front of integral. Then the integration would be nRT integration of 1 over V dV, all right? And for that integration, it will give you a natural logarithm function of V. If you plug in the upper limits and lower limit of the integral, it will give you nRT of line V2 minus V1, oh, divided by V1, okay? So it's the final divided by the initial, okay? There's couple steps missing here for the derivation. So I can show you quickly what steps are missing. All right, so from here to here, so integration V1 to V2 nRT over V dV. If temperature is constant, so you move this all in front of the integral. So 1 over V dV, okay? Then this becomes nRT of line function of V, okay? With V1 and then V2 as the upper and lower limits there. So then you plug in this guy in here and then minus plug in that guy. So nRT of line V2 minus line of V1, okay? Natural logarithm of V2 minus natural logarithm of V1. And when you are doing natural logarithm of V2 minus V1, that is equal to nRT of line of V2 over V1, okay? So there's several steps missing from here to there, but that's how that's done there, okay? And this applies only for when T is equal to constant, okay? So that means the temperature is constant for this process. For temperature is constant, PV is a parabola, so look like this, okay? Just goes down like this on the PV diagram, okay? All right. So on the PV diagram, if the gas system goes from initial status to a final status, say from A to C, there are several different processes you can take. Okay, so you can take the parabola curve here, which means temperature is constant. You can take from A to B and then from B to C, or you can do from A to D and then from D to C. Okay, you'll end up at C through all these three different processes. Okay, but would the work done be the same or not? Okay, so let's take a look here on these three different processes and see what's the work done through them individually. Maybe I can stop sharing there. Okay, so from A to C. Okay, so let's take the first pass off from A to B to C. Okay, and then see what's the work done through that path. We'll be starting with this differential equation here to start with, and then apply this to this pass and that pass. Okay, so from A to B, in this case, so this is a PV diagram, and then so let me see the parameters first. So it's P1, P2, and then V1, V2. Okay, P1, P2, V1, V2. Okay. So during this process, the P is constant. Okay, from A to B, P is constant. So you'll be integrating P dV from V1 to V2. P is constant, can go out of the integration. So then this is simply P of V2 minus V1. Okay. Now from B to C, right, the volume doesn't change. Okay. So this is a constant volume process because this is V2. Okay. So then dV for the process equal to 0. So then work will be equal to 0. Okay. So work from B to C is equal to 0. This is work from A to B is equal to that. So the total work, if you are taking the process from A to B to C, then will be equal to just P times V2 minus V1, or P1 actually. Because on this A to B, the pressure is P1. Okay. If you are taking the path from A to C directly, then that's the process we checked on the previous slide. So you'll be doing, again, work will be equal to V1, V2, P dV. Now, T is constant, so it's the nRT, okay, V1, V2. That we just did it over V. So it will be nRT line of V2 over V1, okay? And for nRT, it will be either like P1 times V1 or P2 times V2, okay? nRT, because PV equal to nRT, okay? Now T is constant, you only have changing of P1 and P2, or P1 and P and V, from P1 to P2 and then from V1 to V2. So it'll be this guy. If you take the path of A to D to C, then work will be equal to, from A to D, the volume doesn't change, so that will be 0. From D to C, you'll be doing like integration of V1 to V2, P2 this time dV, okay? So similar to this from A to B, because it's also a constant pressure process. So it will be P2, V2 minus V1, okay? So you can see if you are taking different passes, then the work done by the gas system will be different, okay? All right. So you can go back to the slide here. So our conclusion is work done from different processes are different, okay? Next, let's consider the internal energy of a gas system. So we'll start with a gas system. That's the all. For the internal energy of a thermodynamic, the simplest one will be the gas system. Now, for the internal energy, okay, so it consists of kinetic energy and any potential energy, okay? So kinetic energy we know from the previous chapter for monatomic gas system should be 3 kT, okay, or 3 K sub B, which stands for Boltzmann constant. So 3 kT, because for ideal gas, we are ignoring any potential energy. So the U terms are ignored. So that's 3 kT, okay? Basically, it's the kinetic energy in 3-dimensional. In each dimensional, the average kinetic energy is 1/2 kT. Okay, and then for 3-dimensional, you have 3/2 kT. All right. So then for ideal gas, its internal energy is just a function of the T. All right. And then so this is for a one molecular, right? So if you have m mole of it, you'll multiply by Avogadro's number and then times 3 kBT, which is equivalent to 3/2 of nRT. Okay. So that's the internal energy for an ideal monatomic gas system. Okay. So pay attention to here, it's a monatomic gas system. So there's no vibration of the atoms in a molecular. All right. Next, we are going to check laws of thermodynamics. So we'll start with the first laws here in this section, but actually I think we should start with the Zeus laws here. Okay, so the Zeus law says, so if you have A and B, they are in contact and they are in equilibrium, and you also have B and C are in contact, they are in equilibrium. Then if you bring A and C in contact, they should be in equilibrium as well. Okay, so that's pretty much the Zeus law says. I'll put into equation if T1 equal to T2 and T2 equal to T3, then T1 is equal to T3. Okay. All right. Now let's check on the first law of thermodynamics. So basically, it's a statement for conservation of energy. Okay, so it says the internal energy change of the system equals to the heat change of the system, and then minus the work done by the system to the surroundings. Okay, so in some cases you may see like delta E, or in some textbook it will use delta U instead of E. Okay, but that's about the same, or just different notation. And Q plus, you may see Q plus W. So in that definition, then the W is work done by the surrounding to the system. Okay, so the other way around. But if you define this as work done by the system to the surrounding, then you take a minus. Okay. The differential equation should be derivative of the internal energy change, or internal energy should be equal to derivative of Q minus derivative of the work. Okay, so this is the differential form in that sense. If you have heat added to the system, then your Q will be positive. If heat is removed from the system, Q will be negative. Okay, work done by the system to its surrounding is positive. Work done on the system by the surrounding is negative. Okay, so these are the signs for heat and work in the first law of thermodynamics. All right, we'll take a look on a simple example here. This says a gas system, a diatomic gas system, does 300 joules of work and absorbs 2.5 kilojoules of heat. What's the change of internal energy here? All right, so I think this is a pretty simple one. We can take a look on this together. Do it this way. So you're going to use the equation change in internal energy is equal to heat minus work. It tells you the heat is 2.5 kilojoules. Okay, so times 10 to the 3, and then it says it does 300 joules of work. So then this would be 2200 joules of internal energy change. Okay, should be kind of straightforward on this. All right. So I think we kind of check on like several different processes, but let's take a look some of the common processes here. Okay, so some terminology over here: isobaric, that means you keep the pressure constant. Isochloric means you keep the volume constant. For isothermal, that means you keep the temperature constant. Okay, and for adiabatic, that means no heat transfer happens during the process. Okay, and we'll be looking at these processes one by one. But to make things simple, we usually consider the process as a quasi-static process. Okay, so that means it happens very slow, so that uniform temperature and pressure exists throughout all the regions of the system at all time. Okay, so that's the assumption we are going to make here. All right, let's take a look on the first one, isobaric process. So in this case, then work done by the gas system. So if it's expanding, so then you go from initial to final. Okay, so then according to PW or dW equal to PdV, all right, you integrate. P is constant, so then work is just equal to P times delta V. Okay, the change in the volume. So for example, if you have a piston that can move freely, so if this expand with constant pressure, then the work done by the gas system will be P W equal to P times delta V. Okay. Let's take a look on one example here. The isobaric expansion of water in this case. Okay. So this one says 1 gram of water is placed in the cylinder and the pressure is maintained at 2.0 times 10 to the 5th Pascal. The temperature of the water is raised by 31 degrees. The water is in the liquid phase and expand by the small amount of 1.0 times 10 to the minus 8. Find the work done and the change in the internal energy. Okay, so you need to find work done and then change in internal energy. For isobaric process, work will be just equal to P times delta V. Okay, it tells you P, it tells delta V, so you can calculate this one directly. For this guy, internal energy change, you should be doing Q minus W. So you have W already, you need to figure out Q first. Okay. To calculate Q, you need to use MC delta T, okay? It tells you the mass, 1 gram. C, if you don't remember, is 4186. All right, so let's take a look here. So work is equal to P times delta V because of a constant process, okay? So for A, work is equal to the pressure 2.0 times 10 to the fifth times the volume, just expand very slightly. So you'll get 2.0 times 10 to the minus 3, okay, for that. For internal energy change, you want to calculate Q first, MCWT, okay? Then you can do delta E equals to MCWT minus work, okay? So 1 gram, that means 1 times 10 to the minus 3 kilogram, okay? C is 4186. And delta T, it tells you like 31 degrees minus 2.0 times 10 to the minus 3, okay? That should give you roughly 1.3. That's 129 something, but you can keep 2 digits to be 1.3 times 10 to the second, okay? All right. Okay. So next we are going to check the isochloric process, which means you keep the volume constant. Okay, so if you have a container like this, closed container, then you can add heat to it, but it will not expand. So the pressure inside will change, but the volume will not change. Okay, so the volume is constant in that case. If you have constant volume, then the work done will be equal to 0 because delta V is equal to 0. Okay, so then work will be equal to 0. All right. The next process we are going to check is the isothermal, the one we actually checked earlier when we started the chapter here. But basically, you are going to integrate W equal to dW equal to P dV, and then in doing integration there, okay? So P can be written as NKT over V or nRT over V, then you get result as a natural logarithm function here. So the work done will be equal to either NKT line of V final over V initial or nRT of line V final over V initial, which is actually the area underneath the curve, okay? Here from V1 to VF, okay? Okay, so the last one here, we are going to check is the adiabatic process, which means you have no heat process, no heat transfer during the process, okay? There are two ways you can accomplish this. The first one is you can isolate the system so well, okay? So for example, a very well insulated system. And in this scenario, if there's status change over here, you don't have heat exchange between the gas system to the outside surrounding, either if you are compressing it or if it expands, okay? The next, the second method you can use to achieve this is you can have the process happen so quickly, okay? So one of the demos you can see is this guy. Let me see if I can find this here. Is it in the stock room maybe? So for this, you will have the process happen so quickly, so then there's no time for heat to escape. Couldn't find it. Yeah, we have exactly the same setup, but you can check this up online somewhere. Okay, so basically, this is what you are going to have. You are going to so there's a piston like this. It's kind of insulated well, so that's double layer of walls here, and then you can put a piece of paper, the tissue paper, small piece over there, and you're going to push the piston down quickly. All right. So in that process, you are doing the work to the gas system that's in the piston, right? So you are doing the work there. According to the first law, the internal energy equals to, so delta E equals to Q minus W. You are doing the work to the gas system, so your W is negative. Okay. So then in that sense, if you are doing this so quickly, there's no time for heat transfer. So this is 0 minus a negative work. So then delta E is increased, okay? So delta E is proportional to the temperature of the gas. So in that sense, if delta E increase, the temperature inside increase quickly, okay? And if you are doing this quickly enough, you may reach to the ignition point of the tissue paper. So then you will set that on fire, okay? For diesel engines, actually it doesn't have a ignition like the sparkler. It actually uses this mechanism that the process happens quickly, so then it can ignite the diesel gas, okay, in the chamber, all right? All right. So those are the four process we want to check. But if you have a cyclic process, which means you are starting at point A, you are taking several different different passes, you are coming back to point A. Okay, so there you complete a circle. So it's called a cyclic process. So in that case, because you are returning to the initial starting point, so your internal energy should be equal to 0. Okay, so for the whole process, the work done should be equal to the heat. Okay, that receives. So that's pretty much how a engine works for your car engine. It takes heat, all right, and it does some work. So the heat differences, that means the heat it takes in minus the heat it dumped out, that should be equal to the work done, okay, for the whole process. All right. We'll take a look on this example here. It says an ideal gas initially at 20 degrees Celsius and 200 kilopascal has a volume of 4.0 liters. It undergoes a quasi-static isothermal expansion until its pressure reduced to 100 kilopascal. It's asking you to find the work done by the gas and the heat absorbed by the gas during the process. So it says it's an isothermal process. So that means T is equal to constant, okay? And it also tells you this is an ideal gas. So you can apply PV equal to nRT. All right. For isothermal process, we checked before that work done should be equal to either NKT or nRT natural logarithm of final divided by initial. I'm going to use 2 as final, 1 as initial, okay? Let me see. I think you have enough information here for the problem. Now for ideal gas, also remember that internal energy is determined by the temperature. So it's basically 3/2 of nRT, okay? All right. So the first part asks us to find the work done, and we know work done for an isothermal process is equal to this. Or you can start with dW equals to PdV. Okay. You should be able to do this. So work done then will be equal to that, equals to integration of P dV. Okay. According to this guy, P is equal to nRT over V. Okay. So integration of nRT over V dV. The same process, you'll get to this result of nRT ln of V2 over V1. Okay. So I think we have done that. I'm not going to repeat it, but here, it tells us V1, right? Initial volume. It didn't tell us the final volume. It tells us the temperature. It didn't tell us the N. R is the constant 8.31. But according to this guy, so then P1 V1 is equal to nRT, right? T is constant. So you don't have to know M. Of course, you can solve for M from here because it tells you T, the temperature. You can solve for M and then put it back here. Or you can just simply do PV, P1 V1. Okay, so this is equivalent to P1 V1 line of V2 over V1. Okay, so now to calculate the work, you just need to figure out V2. All right, now if T is constant, so then P2 V2 should be also equal to nRT, right? So P1 V1 then equals to P2 V2. Okay, so if you divide both sides by V1, okay, that will cancel out. So then you have V2 over V1 here. You can move this guy to the other side. Okay, so P1 over P2 then equals to V2 over V1. Now it tells you P1 is equal to 200 Pascal, P2 is 100 Pascal. So 2 over 1. So then this is equal to 2, right? Or 2 over 1, right? This is 200. This is 100 for P2. Okay, 100 for P2, 200 for P1. So then V2 over V1 is equal to 2. Okay, and that's basically what you need here. So this is equal to 2. All right, so you can do P1 200 kilopascal times V1 4.0 liters. So that means times 10 to the minus 3 meters cubed, line of 2. Okay, natural logarithm of 2. So in that sense, work is equal to, if you plug in all the numbers, should be equal to 555 joules. Okay. Now, as I mentioned, you can also like solve for M and then use nRT instead. Okay. And then you can solve for V2 first. And then plug in the numbers, but you will get this number, okay, for the work done. All right. For B, it asks you to find the heat absorbed by the gas during this expansion. So looking for Q. All right. Now, to solve for Q, you will have to use the first law here of thermodynamics. Delta E equals to Q minus W, okay? While delta E is just determined by the temperature, so E is just determined by the temperature. So if there's no temperature change, so that means delta E is equal to 0. Okay, so this guy is 0. So if this is 0, then Q is going to be equal to W. Okay, so Q then is equal to W. It's the same 555 joules. All right. So this is for ideal gas. All right, so any questions you guys might have? All right, if that's clear. Um, so we are kind of going back to chapter 2. That's this one section we didn't talk about, but I feel like this is more related to the um, content in chapter 3. So we'll go back here. Okay, so for the heat capacity and equal partition of energy. Okay, so now remember when we define specific heat capacity, that's defined as Q equal to MC, the mass times specific heat times delta T change in temperature. Or in this equation, you rewrite that so that C equals to 1 over M times Q divided by delta T. Okay, now for a gas system, all right, we can write that instead of writing the mass of the gas, we are using typically we're using number of moles or number of molecules there. So if we can rewrite the equation using moles, because mole is proportional to the mass. Okay, so you're just having to do some conversion here. So then this C over here, it's called the heat capacity, molar heat capacity. Okay, it's called the molar heat capacity. So that's heat capacity per mole instead of heat capacity per kilogram in this case. Times the change in temperature. The fact that you have V, volume, stands for volume here, that means if this is a constant volume process. Okay, so then you do that way. All right. So then Q is equal to M times C sub V delta T. Now, rearrange the terms, you get CV equal to 1 over M Q over delta T, okay? If your V is constant. So if this is an ideal monatomic gas system, if you have M moles, the internal energy, as we checked before, we are just considering the kinetic energy is 3/2 of nRT, all right? So if your volume does not change, so that means it doesn't doing work, right? So W is equal to 0. So delta E then is equal to Q. For first law of thermodynamics, it says delta E equals to Q minus W. So volume doesn't change, W is equal to 0. So then these two are equal to each other, okay? So therefore, Q then is equal to 3/2 of nRT. All right, so which means, if you are looking for change in Q, delta E is change in Q. So then this CV is equal to 3/2 of R. Or maybe it's not so obviously. I can show you. So just considering kinetic energy, 3/2 nRT. So then change in internal energy should be equal to 3/2 nR change in T, right? Constant here, moles wouldn't change. So if this equals to Q, which is defined as C M times CV times delta T, so then this guy equals to that guy. All right. Then you have CV equals to, here. So then CV equals to 3R, 3/2 of R, okay? Because N and N cancel out, delta T cancel out. CV equals 3/2 of NR. 3/2 of R, sorry, okay? And that's because it's coming from the three dimensional motion of the molecule. Okay. So we can conclude that if you have three-dimensional motion, then the degree of freedom for the movement for the motion is 3. Okay, so using the degree of freedom, so then d equals to 3 for a constant volume, you have that. Okay. Now, in additional to the motion of the object, if you have say diatomic molecular gas. Okay, so then between the two atoms of one molecule, there's also vibrational energy that you want to consider. So then that adds to more degrees of freedom. Okay, so for a diatomic, this is for single monatomic gas. Okay, so then you'll just consider three-dimensional translational degrees of freedom. For two atoms molecular, you have rotational degree, 2 or more degrees of freedoms there. Okay, so then in that case, CV will be equal to 5/2 of R. Okay, so for diatomic gas, if you introduce more degree of freedoms, then it comes there will be the CV will increase. Okay, so basically to summarize, if you have monatomic gas like this ones, degree of the C of V should be 3/2 or 1.5 of R. Okay, so if you do CV divided by R, it gives you 1.5, 1.5. These are experimental data. Okay, so for diatomic, this is 2.5 roughly. For this is about 2.5. For nitrogen is about 2.5. Oxygen about 2.5. This one is a little bit different, 2.8. Okay, still close to 2.5. For three atoms or triatomic gases, then this is about 3.5. Okay, 3.5 here. Now this one is a little bit smaller because it's not symmetric. Okay, but in that sense, roughly about that. Okay, so one monatomic is 3/2, diatomic is 5/2, triatomic gas is 7/2. All right. For solid, the degree of freedom is 6. So then it's 6/2 is 3 times R. Okay. Yeah, I think we already run out of time, so we'll stop here for today.